So, what is important when we really look at the thermal sensors that we are talking of for temperature measurement, particularly non-contact based measurement of temperature, several types of sensors are available, right, for different applications. And we actually focused on one important thing, that was with respect to measurement of temperature indirectly using the neodymium magnets, and by employing Hall sensors we were able to measure the change in magnetic field. We will come to that. But before we actually look at temperature measurement indirectly, let us just finish off the story on the things related to IR thermometers, which are basically used for non-contact applications. Now the point really is, if you first thing is you have to understand the IR thermometer, and you have to spend sufficient amount of time trying to understand the physics behind it as well. If you really want to look at what a IR thermometer is, let us spend a little time trying to understand. You must have all seen thermocouples, right. Essentially a IR thermometer, what is its business? If you understand from a 40,000 feet view, you will understand that you need a device which will absorb IR heat, right, and it has to give you some voltage at the output. So you need to get some V out ultimately, and how do you get this V out? How do you get to this V out? Let us draw the picture of a simple thermopile, which is essentially a set of series connected thermocouples. So for that, let me draw first the picture of a thermocouple. Thermocouple essentially you can denote it like this, and essentially you take it to a amplifier and you generate V out here, right. So this is the crux of the issue. This is essentially the IR absorber, okay. This is the IR absorber, which is essentially absorbing all the IR heat, and what is critical is this part. What is critical is this part. This is Tref, temperature reference, okay, and this is the actual temperature that you are measuring. A simple expression is, going back to this thing, is a simple expression here is, just look at these systems here and you can write a very simple equation which simply says V out is equal to S times Tx minus Tref, right. So let me write it a little better so that you will be able to read it. Ref, right. So this is Tref. S is nothing but the Seebeck coefficient. Now you could take it to any level, right. If you actually ask me, you must know the physics behind the process, this process of absorption, and all of that are governed by Planck's law of black body radiation, right, and Stephen Boltzmann law of radiative heat transfer. So again I want to stress a very important point. Why am I doing all this? To give you a feel that when you talk about IoT and design for IoTs, and you are looking at sensing, you must know the principle behind sensing, the physics behind the sensing, and use this together to determine the kind of sensor required for a given application. You must know this, there is no other way except going into the details of both of them in order to arrive at the kind of sensor, kind or type of sensor, call it type of sensor required for a given application. So, this is a very important thing. So, when you say design, you must have many choices, many design choices, and you pick the best choice, and the choice, the way you pick will depend on the kind of application that you have in mind, and based on that is what you would ultimately decide. For example, I must show you another type of non-contact way of measurement. Perhaps you can look it up yourself, in the next class I will show you. There is another kind of sensor called the PIR sensor. Okay. This is essentially a electronic sensor which is based on the principle, the physics behind this is pyroelectricity, right. This is, what does this mean? This principle here is pyroelectricity. Physics indeed is the physics we will get to a little later, but at least it is based on the principle of pyroelectricity, and it is essentially the ability you can look up these definitions anywhere, in fact even Wikipedia will have this definition. So, I am just trying to tell you from very simple terms, ability of certain type of materials to generate a voltage, So, you can see it is a voltage generator. When you heat or cool, that is also important. Okay. So, you could essentially, this is pyroelectricity, essentially what I have shown you is this is what it is, but a PIR sensor uses this principle, and today you get this PIR, and for some reason it is very commonly called passive infrared sensor. Although the principle is based on pyroelectricity, it is called passive infrared sensor. This PIR sensor essentially is an electronic sensor, and it means that IR light, essentially it is also trying to capture the IR heat from objects when it comes in its range. So, the PIR sensor will be something like this, with a lens in the front, and there is a possibility that and there is a lens, okay, and the lens essentially will ensure that the PIR sensor has a range. A good range for a PIR sensor means you must have a good lens, and there are different types of lenses. We will not get into the detail at the moment, but the real trick for a PIR sensor to work satisfactorily means lens. So, you must very carefully choose your lens if you are choosing a PIR sensor for heat detection, for detection of humans. and for example detection of humans is just one simple trivial way of saying what a PIR can do. What it can actually detect is motion, right. It can detect motion. You might have seen many applications where motion is actually detected to do a few operations. For instance, if you walk into the corridor of a hotel or you walk into a public place where there are public, let us say, rooms or common facilities where normally you do not want power to, you do not want the systems to have the lights on all the time, lights on only when they detect presence of humans, right. You want to switch on the lights, keep the lights in the room as long as humans are present, right, only when they detect presence of humans. So, for these applications you essentially tie a PIR, you essentially interface it, you interface the electrical part like turning on, turning off lamps and all that to a PIR sensor, and you will see that a PIR sensor generates, sorry this is incorrect, PIR sensor actually generates a signal like this and a signal like this, okay. Essentially you will basically have two elements in the PIR sensor, and the elements, when both the elements, we will call them plus and minus, essentially when these elements essentially see the same amount of IR heat, no signal is generated. But if plus sees a higher IR energy, it will generate a positive going pulse, and the reverse will happen when the negative sees a certain amount of energy higher than the positive, and you will essentially end up with a negative going voltage peak, right. So, essentially you will get signals like this. These signals are taken, processed, and essentially you will generate a digital 1 or a logic 1 or a logic 0. 0 means human is present, and 1 means human is present and 0 means human is absent. So, this is in a sense what a PIR sensor can do to us, right. So, you can use non-contact. So, the big summary is you can use non-contact, oops, let me draw it again, let me write it again, non-contact IR in different ways for different applications. You can use PIR, you can use thermocouple or thermopile, okay, and you can measure and so on and so forth. You can use different types of sensors for different applications. So, in other words, the big summary indeed is that you may have to, before you decide the kind of sensor that you want for an application, you have to first understand the principle of the sensor, because you will know whether such a principle is what the application actually requires, the application is actually based on that principle, or and also the physics behind it, right. I will give you a very simple example. If the principle, if the application indeed is about motion detection, which we just said a PIR can do, then I would use a PIR sensor, and I just simply detect a motion 1, no motion 0, presence 1 and no presence of human 0. If I am really interested, and I would use the principle of pyroelectric effect, and if I am using pyroelectricity effect, and if I want to use measurement of body temperature, I would say core body temperature, I will then use thermopile. You see now, thermopile, and actually measure the temperature. Here you are not measuring any temperature, you are only using it for motion detection, but here you are actually using it for temperature detection, for measurement of temperature. And if you say core body temperature, it has to be 0.1 degrees accuracy. They should be, you should maintain a 0.1 degree accuracy for all these. So the you really, it is about medical accuracy, right. So let me rewrite it. So if you are talking about medical accuracy, it has to be in the range of so high accuracy has to be there, it has to have 0.1 degrees Celsius, and it has to have very good resolution as well, resolution. Okay. So this I sometimes it is in the order of 0.2 degrees Celsius. These are two separate I would say specifications for sensors, for particularly thermopile based sensors. If you are looking at for the measurement of core body temperature, you will have to look for medical accuracy. Medical accuracy is important. In general, if you are talking about thermopile based sensors, you may also want to look at resolution, which is a very important thing. So that is the key here. So what I wrote here is interesting. I wrote core body temperature. If you are interested in body temperature, right, so which is not really core body temperature, you recall that if you talk about this core body temperature non contact based, we said arterial temporal artery is what we are going to use, temporal artery. We are going to scan the temporal artery, I will say scan the temporal artery and perform a very simple analytics on the data that you acquire through the medical grade sensor, and then you decipher, you actually figure out, you actually pull out the core body temperature. If you are interested in just body temperature, many ways of doing it. We also spoke about the liquid crystal thermometer. Okay, this is called the LCT thermometers, which are also quite cheap, but they do not give you medical accuracy. Let us say you are interested in measurement of the incubator, measurement of a small enclosed place of a baby incubator, then the sensor here has to take care of mapping the whole space within the incubator, right. I will just denote here. So it has to profile the whole system, and a complete profile of the incubator has to be obtained, and you are measuring ambient, you are not measuring the core body temperature, because you are using the measurement of this temperature here for either switching on the heater, okay, the heater in order to keep the baby warm, or in order to control the temperature. So, you need a different type of sensor here. So, it's interesting that you can do, depending on your application, your sensors have to be chosen, different type of sensors are available, and also very importantly you have to look for the data sheets very carefully. Data sheets have to be looked up carefully. You will have to look at accuracy, you will have to look at resolution, you will also have to look at the sensitivity, thermal sensitivity basically, right. Normally the thermal sensitivity is denoted by noise equivalent temperature difference or differential. So, this is a parameter which you may want to look out. So, these are, I think, the most, in my opinion, are the most critical things, specifications that you will have to look out when you are trying to use, when you are trying to make, when you are trying to use a temperature sensor for different applications. Let us now move on and take an example of, we started this lecture by giving you an example of this bearing, and when you start rotating the bearing you have neodymium magnets here, and you heat the bearing, or rather when the bearing gets heated up, it changes the magnetic field, and this change in magnetic field essentially is captured by this Hall sensor which is sitting here, and it is called captured by this Hall sensor board which is sitting here. Maybe I should just put it this way so that you actually see a chip which is here, and that chip is essentially interfaced to this little PCB, which essentially has very interesting components along with it, and we will describe this nice little components which are there on this PCB to give you an idea, to give you a feel of what essentially it means to design an IoT system. What is also interesting, and we mentioned this last time, is this coil here. Let me align it back, this coil here, which essentially is used for harvesting purpose. You have a rotating magnetic field caused by this bearing here, bearing is rotating, and then you have these arc neodymium magnets, the magnetic fields of lines of force are being cut, captured by this coil, and essentially a small voltage is developed here which can be used after suitable power conditioning to actually power this board, and all the energy is actually stored on this capacitor you see here. This is a super capacitor which essentially holds the power, holds the charge, holds the energy to drive this electronics and make available the temperature of the ball bearing suitably to a driver perhaps on the dashboard of his system. Let us run through the nice thing about this board and what exactly goes behind, so that we will be able to connect it to the next set of lectures which we may have to begin specifically on the power supply section. So, let us take this example of the system here that we see is, you will see that I will show you the measurement results that we did for that experimental jig which had the bearing. I show you two pictures here. First thing is the temperature cycling graph. This is essentially the temperature cycling graph which is on top, and what you see bottom here on the left side here is the magnetic cycling graph. Unless there is correlation between the two, there is no way by which you can actually measure the temperature of the ball bearing indirectly using magnetic field. So you can see that we made this measurement over let us say about 40 minutes or so, and we started heating the bearing race of the bearing, and the temperature was made to rise from 30 degrees Celsius to about 120 degrees Celsius. As you can see, this indeed is 120 degrees at this point. So this is 120 degrees here, and this is 30 degrees here. As I mentioned, this is with respect to temperature cycling graph, and this is with respect to the magnetic cycling graph. You can see that I will not even get into the detail of the units, but I will just tell you about the analog to digital converter values, which actually changed from 450 to roughly 464 and went back to 455. Okay, these are the 3 points. More or less the profile followed by the change in magnetic field also sort of mimics the change in actual temperature of the bearing. It was not easy to do this because you need to use a thermometer to make this measurement. So we used a thermometer, an industrial thermometer, contact based. Please note, we did not use IR, we used a contact based thermometer, and this of course is just the Hall sensor values, right. This is directly coming from the Hall sensor, directly output from Hall sensor. This is output from sorry, let me write it properly, output from thermometer. Very good. So if you now see, this is an interesting result again, it is just the same result shown in a slightly different manner. You can see that the temperature, the y axis is actually the temperature and the x axis is the ADC value. This is physical temperature that we measured using the contact based thermometer, and these are the ADC values that we got through the indirect method of measurement of the magnetic field. You will see that there is a nice range of change in the ADC values from some initial value of 580 to another point down here, which is roughly 587. So 580 to 587 was a nice range over which we were able to see the change in ADC values with respect to the change in temperature. You may be a little confused, why did I change, why is it that it changed here. I said 450 and it went to 400 and roughly 464 and went back to 455, and in this result we are getting different values. Well, the reason is they were done at 2 different times, and they were essentially the ADC values will largely depend on how the magnets are oriented on the bearing race, and so this small variation, slight change in values is not surprising. What is important is if you start making a measurement from an initial value, it should essentially show that you are able to see a change in the ADC value. This is important. There must be a change in the magnetic as the temperature decreases, this ADC value should go up, and that is what is very important. and so that is, so just to give you a possibility that if you make such a measurement, do not be surprised to see that in one measurement you get different values, and compared to one measurement, and another time you get a different range of values. How did we make it work? This is a very critical slide. How did we ensure that the whole system really was able to, so this PCB that I showed you, this PCB for instance that I mentioned to you, what does it have on it? Let us see in detail the different blocks. So let me put back this PCB.